Lesson 24 continued. Example number 7. We're going to do very quickly because you've seen this. It's very similar to the elevator problem. You're dropping a piece of paper. Oops, here's your piece of paper. It's got gravity pulling it down. And what's pushing it up? Nothing was pushing it up, then it would accelerate at 9.81 meters per second, and that would be the answer to the question. Air friction is pushing it up. So we are going to say F. F is the friction of the air that's pushing it up. Determine the acceleration of the paper. So your net force equals your force of friction plus your force of gravity. And obviously, this paper is falling to the ground, so we're expecting to get a negative answer for our acceleration. Let's do this one the same way that we did example number 6. In other words, we'll do it in one step. So we'll go MA equals FF plus, now if you want FG, you can flush that out to MG right away. Divide both sides by M, and you get FF plus MG divided by M. Don't cancel out the M's, whatever you do. You can't do that. You can only do that if M was common to, if it was FF times M also. And then just fill in the numbers. The frictional force is 4.71 times 10 to the negative 4. Mass, oopsie, plus 7. Plus the mass of the paper is 500, or 0.05, 0.0, come on, space again. I should be learning my lesson. 0.05 times 10 to the negative 3. That's how I'm going to write it in kilograms. I'm just going to add times, including a 3 to the end of it, times gravity, which is going to be negative. And I know that's going to happen, so I'm just going to write it here. All divided by the mass, 0.05 times 10 to the negative 3. All right, just stick all that into your calculator. And you are going to get an answer of negative 0.39 meters per second squared, which we're just going to say as 0.39 meters per second squared down, because the negative doesn't tell us enough about the answer. All right, on to something that's a little different, and this is where we have two boxes attached by a thin wire. Person pulls on the wire attached to the yellow box. There's a force of friction of 213 newtons. Determine the force applied to the box as they accelerate to the right at 2.45 meters per second squared. And in problems like this, since both objects they're being pulled on a string and they're tied together, so logically both objects accelerate at the same rate, and so we really just treat them as one object. Okay, so when we draw the free body diagram for this, we don't draw the two masses. We just draw one mass of 30 kilograms. And it has an applied force pulling it that way. It has a frictional force going opposite the direction of motion. And of course, it has the two other forces on it. The force of gravity going down and the normal force going up, Fn normal force, not net force. For net force, you have to write NET. But in this case, the normal force and the gravitational force are equal and opposites because the object is not accelerating up or down, and therefore you could just leave them out if you wanted. But that's the fully correct free body diagram. The only ones that are going into play in terms of accelerating the object are FF and FA. And just like vectors, we do everything in direction. So we're going to have an F net in the horizontal direction, an F net in the vertical direction. It's just that the F net in the vertical direction is 0, so we don't even bother with it. So we're just going to deal with F net in the horizontal direction. The net force equals FA plus FF. FA being the applied force. Now in this one, it says determine the force applied to the boxes as they accelerate to the right at 2.45 meters per second. So we're solving for the applied force. So you're going to get the net force minus the frictional force. Now here's where positives and negatives can really mess you up. So you have to be very careful because now in the equation there's a negative sign. And that negative sign right here, this minus right here, is a result of rearranging in the equation. So we can't just ignore it. But we still have to acknowledge that the frictional force and the applied force are in opposite directions. Now, in this specific case, it's not going to make too much of a difference because when we flush it out, we are going to say that the net force is MA, and the frictional force is already made a mistake. The frictional force minus is given to us already. So MA, we have the mass, which is going to be 30. We have the acceleration, we're going to say 2.45 in the positive direction to the right, minus, now what do we do for the friction force? Is it just minus 213, or is it minus negative 213? And the answer is negative. You must put the negative in there. Minus negative 213, because we already said that the box is accelerating to the right, and therefore to the right is going to be positive, and therefore any force to the left must also must be negative. Okay, so that's very important. Put that negative sign in there, and then we stick it into the calculator. It's 30 times 2.5 minus negative, or you could have just put plus 213, and you get 287 newtons is the answer to the question, the applied force. Just before you go to the next question, just think about the logic of that. You ended up, in fact, adding this, which makes sense because if you apply a force and then you increase the frictional force, you're going to have to add that frictional force to the applied force to get the net force. So just think about that in your head for a while. But it's logical that you ended up adding the frictional force to get the applied force, right? Because if that frictional force was, if there was more frictional force, then clearly you would have to have more applied force. So this number would have to increase. So you do end up adding them. Okay, on to the infamous Atwood's pulley question. So Atwood's pulley, we've got a mass of 12 and a mass of 7. So please read over the question, but I'll just draw a diagram so you can see what an Atwood's pulley question looks like. It looks like this. You have a pulley, and then you have a weight on one side, and you have a weight on the other side. And this one is 12, and this one is 7.5. And then you let go. And when you let go, clearly the 12 is going to go down and the 7.5 is going to go up. All right, so this is an Atwood's pulley question, and we're trying to determine what the acceleration of the two masses is. Again, let's just talk about it and think about it before we solve the problem. So if there was no 7.5, if there was no 7.5, if there was nothing on the end, what would the acceleration of this be? Well, obviously it would be 9.81 meters per second squared. But there is a mass. So what is the mass on the other side? What's it going to do? Well, it's going to make this one accelerate at a value less than 9.81. They kind of counterbalance one another. If this one over here was 12, what would the acceleration be? 0. It would be in equilibrium. But since it's not 12, since it's less than 12, then this one's going to go up, this one's going to go down, but it's not going to go down at 9.81 meters per second squared. What forces are acting on this? Well, the only force acting on each mass is going to be gravity. Gravity. gravity is pulling this one down and gravity is pulling this one down. But this is the trick about Wood's pulley questions, is once again, we know that whatever rate this one accelerates down, this one will be accelerating up at exactly the same rate. So we're going to treat it as one mass, and this is how we're going to do our free body diagrams for Atwood's pulley questions. We're going to combine the mass, and then we're going to have two forces, and we know one's accelerating down and one's accelerating up. So we're going to have two forces in opposing directions. And to simplify things, we're just going to do it like this. We're going to have an FG1 over here and an FG2 over here. Okay? And just so they're along the same line, even though in the diagram they don't appear to be along the same line. But we know that they're counteracting one another, just like a tug of war, right? So this one's pulling down and this one's pulling down, but this one's pulling down also gravity, but this one's pulling harder. So what happens in a tug of war? The 7.5 ends up going the way that it doesn't want to go. All right, once we've got the free body diagram, then it becomes quite straightforward. FG1 plus FG2, F net, and again, we're trying to solve the acceleration in this problem. That is true. Let's do this one in 2 steps. So we'll just solve for the F net first, and then we'll solve for the acceleration. This is going to be mg1. This is going to be mg2. Oh, I should have put actually m1g and m2g, but that's okay. You get the idea. The mass of this one is going to be 12. Okay, now you've got to be really careful here. The forces are going in the opposite directions, right? So to sort that out, we can do this. Negative 9.81 plus the mass of the second one is 7.5. Now, what are we going to do for the gravity here? Clearly, since they're going in opposite directions, this is where we have to break one of our rules for gravity. This is where gravity, we're actually going to say, is going to be positive, even though it's not. But because of our free body diagram, because they're going in opposite directions, we need some way to account for that. That's how we're going to account for it. So we're going to go 12 times negative 9.81 plus 7.5 times 9.81. And we're going to get an answer of negative 44.145 newtons. So that's the net force in this problem. And the negative simply means that the 12 is going to be going down. And then we're going to find the acceleration. Acceleration equals net force divided by the mass. The force is 44.145. I'm not putting the negative there because I know it's down. I can deal with that at the end. What do we use for mass here? We use the whole thing, 19.5. What's we divide that? We get 2.26 meters per second squared is the acceleration. So that means it says determine the acceleration of each mass. So we can say that the 12 is going to accelerate down at 2.26 meters per second squared, and this one's going to accelerate, the 7.5 is going to accelerate up at 2.26 meters per second squared. Okay, and that was an Atwood's pulley question. Now there's one more. There's a Fletcher's trolley question, which is not in your notes, but it's very important you do it. That's going to make for a really long video, so let's just do it anyway. Here we go. Here's an Atwood's pulley problem. This is number 9, question 9. Sorry, this is a Fletcher's trolley problem. Question 9 on page 158. Page 158. Let's go through this. If we were in class, we were doing a lab on this, which is why I insist on going through this question, but it is also a question that appears frequently on quizzes and unit exams. So let's do it. And it's similar to Atwood's pulley. We have a 4 kilogram oak block on a horizontal rough surface attached to a block going down. We have a force of friction of 11.8, and we wanted to calculate the acceleration of the system. So once again, we're going to do a free body diagram, and that free body diagram is going to treat the entire thing as one mass. So we have two forces. We have the force of friction pulling the system this way, and what's pulling the system in the opposite direction? Gravity. Gravity. So in other words, we're doing that. Now, of course, gravity is going down and the object is moving in a horizontal direction, but you have to think a little outside the box here, right? It is the gravity pulling on this one that is causing this to move horizontally. So we consider them, even though they're acting at a 90-degree angle to one another, one's moving down and one's moving to the right, we consider them to be along the same line. Okay? And what do? Return the acceleration. The net force equals the frictional force plus the force of gravity. Let's do this in 2 steps. So the frictional force is going to be 11.8, and we're going to make that. Oh, we're going to make it negative, or should we make it positive? That's a tricky question, isn't it? Not a negative. Let's make it positive. Plus the gravitational force. Now you got to think about this. Gravity, of course, is acting on both of the masses, but gravity acting on this mass is equal and opposite to the normal force. So in other words, the gravity pulling this mass, this 4 kilogram mass down, is irrelevant because the table is pushing it up with an equal and opposite force. And so what is the only mass that's contributing from a gravitational perspective? This one here. So this is where you have to go. M is going to be 2, and G is going to be negative 9.81. That's why I made this one a positive. I made the frictional force positive just because I like putting a negative for my gravity there, but I needed those forces to be in opposite directions. So stick that in, 11.9 plus 2 times negative 9.81. That gives us a net force of negative 7.82 newtons. And we want to calculate the acceleration of the system. The acceleration of the system, acceleration equals the net force divided by the mass. So that's going to be a 7.82 divided by the mass. What mass do we use for this one? For the acceleration, we always use the mass of the whole system because they're both going to be accelerating at the same rate. This one in this direction, this one in this direction, but it's going to be the same magnitude. So that's going to be 6. We divide those by 6, we get negative 1.30 meters per second squared is the answer to that question. Okay, and you don't really need the direction because it says determine the acceleration of the system. For B, determine the tension in the string. So the tension in the string is basically here, right? You got the tension going up. And for this part, for part B, the tension, if you draw your free body diagram, this is what it looks like. Ft going up, Fg going down, and the tension in the string is entirely caused by this 2 kilogram mass and gravity. So really, we're kind of just isolating this part of the system when we do the second question. But now that we've got the acceleration, it's going to make it nice and easy because it's going to be your F net equals Ft plus Fg. In this case, we're solving for the tension. The tension plus Fg. oh, sorry, minus FG. Again, be very careful with your signs. Don't do what I just did. Minus FG. Your F net is going to be MA, and your FG is going to be mg. And since we're only dealing with the mass that's affected by gravity, they're both affected by gravity, but only this mass is being affected by gravity, causing the system to accelerate, then we have to use the 2 only. And the acceleration is negative, oh, sorry, we're going to use, okay, now, again, let's think about, oh, let's not think about this. Are we going to use a positive or a negative here? Which way is the system accelerating? Or which way is this thing accelerating? It's accelerating down. So we have to use a negative there. Minus the same mass, because in our free body diagram, we've only got that one mass there. And is this going to be a positive or a negative? It's going to be a -2. The mass is accelerating down. Gravity is pulling it down. So they both have to be negative. So you can see how this can get very confusing with the negatives. Times -1.3 equals -2 times -9.81 equals, and the answer is 17 newtons. Okay, so that's a Fletcher's trolley problem. That's one that you're going to want to practice because, as I said, it comes up quite often on unit tests and exams. All right, that's it. Oh, that was a long lesson, 20 minutes. See you in the next one.